In this lesson, I will explain what is stereoisomerism, starting with the definition of stereoisomers. The compounds have the same structural formula but are different arrangement in space. When this type of condition occurs, so they are called stereoisomers. And when we talk about the stereoisomerism is of two types. Number one is called geometric isomerism, or it give us two geometric isomers, and second type is called optical isomers, and I will explain one by one very deeply. So watch this video till end, starting with geometric isomers. Now in front of you can see the molecule of alkane. It is 1,2 dichloroethane, and the second molecule is 1,2 dichloroethene. So what is the difference between these two molecules? The first molecule have single bond and the second molecule have double bond. Now you can clearly identify the difference. So when there is a single bond and when there is double bond, so what kind of difference we have? Now you can see the single bond is rotatable but the double bond is not rotatable. When the single bond is rotatable, then the position of these groups are not fixed. So when the position are not fixed, so there will be no isomerism. But when we talk about alkene, in alkene, as the double bond is not rotatable, so these group will have fixed position. So when they will have fixed position, so if I show you another type of arrangement, now you can see in this arrangement what kind of difference you can see. If I just compare both of them, now you can see here the chlorine atom are in alternate position, but in the second molecule the chlorine atom are in adjacent position. So we identify this type of isomer as trans, and when the same group atom are in adjacent position, so we identify this as cis. So this is the way we basically identify geometric isomers. Now moving toward the definition of geometric isomer. As this occurs due to the restricted rotation about the carbon-carbon double bonds, so it called geometric isomerism. So this is the definition of geometric isomerism. So remember that whenever there will be restriction in the rotation, this kind of isomer will occur. If I just tell you another thing, that in cyclic compound, carbon-carbon single bond are also not rotatable. So in cyclic compound, this type of isomerism also occur. So I will explain this thing later. Okay, moving forward. Okay, now can you identify which type of isomer is this? But what kind of difference it has? Now you can see the both identical group are attached with the same carbon. So do you think it will form another molecule isomer if I try to exchange their positions? So do you think I will get the different molecule? Answer is no, that I cannot make another type of isomer by the changing of these two group, because they are attached to the same carbon. So always remember, the stereoisomer occurs when the two double bonded carbon atom each have two different atom or group attached to them. Let me show you some example. Now in front of you, in the first example, you can see this methyl group. Both of the methyl group are on adjacent side, and in the second example the methyl group on alternate position. So what do you think this one is? Yes, this one is cis, this one will be trans. And when we talk about this in the third example, now you can see both the methyl group or identical group are with the same carbon. So this will be not a geometric isomer. Okay, another example here. Now you can see the bromine atoms are on adjacent carbon. Here the bromine atoms are on alternate position. So this will be cis and that would be trans. Okay, let me show you a very important example or very interesting example. Now what can you see here? Yes, there is no carbon-carbon double bond, but there is nitrogen-nitrogen double bond. So criteria, the logic will be the same, because the identical group are on alternate position. So I will identify this one as trans, and here the identical groups are on adjacent position. So I will identify this one as cis, and because of the double bond, the rotation is not possible. So this this is not necessary that the always carbon atom should be there for the cis trans isomerism. Okay, moving forward, let me talk about the cyclic alkane cis and trans. Okay, remember that if a ring has two substituents on it, or you can say the identical group on it, if they are on the same side, so we will identify as cis, or the opposite, for the opposite side we will identify them as trans. Now you can see here, let's suppose these are H. Now what do you think? Here the methyl group on the same side, so I will identify this one as cis. When the methyl group will on the opposite side, so I will identify this one as trans. Okay, let me show you another example here. This one is cis because the methyl group are on adjacent side or same side, so I will identify this one as cis. But in the case of trans, you can clearly see these methyl group are on opposite sides. So this was the cis trans isomerism in alkane. Okay, let me show you some more example for better understanding. Now what do you think, which one is cis, which one is trans? Yes, this one is cis, this one is trans. Why? Because here we have the same group on the same side, here the same group on opposite side. And another example here, so what do you think, this one? Yes, this one is also cis, this is the same example basically, and this one will be trans. And let me show you another example. Yes, this one is not cyclic, but it is aliphatic. Now what do you think? Yes, you can see these are identical group on the alternate position. Here these are identical group are on adjacent position. So when we have a group on alternate position, so it will be trans and that would be cis. And the last example for the geometric isomerism. So what do you think, what kind of isomer is this? Now you can see two same identical group on the same carbon. So what do you think? Yes, two identical group on the same carbon, not stereoisomeric. So this is not cis or not trans. Okay, if you have any question regarding cis trans isomerism, you can ask me in the comments. Okay, let me explain optical isomerism. Now let's talk about the optical isomerism. Okay, as the name is optical isomerism, so we think it will be related to the light. So when we focus on the light, remember that a light always have random orientations. Let me explain it more, that it move in all direction, in all plane, in all orientation. So if we have a specific filter that can change, that can filter it and make it a plane polarized light. So what is plane polarized light? Basically a light which only travel in a single plane. Okay, if I give you a daily life example, everyone has seen the laser light, red laser light or green laser light. So basically they are plane polarized light. Okay, now we have some compounds show the response to this plane polarized light. So now you can see these two molecules are identical, even they are identical, they have same group. So you can see the central, if I say this central atom is carbon atom, here the carbon atom attach hydrogen, chlorine, iodine and bromine, and this one is also a carbon atom, and this carbon atom also attach hydrogen, bromine, iodine and chlorine. So both are same molecule, but what happens when a plane polarized light passes through each of them? One can rotate plane polarized light clockwise and other will rotate the same plane polarized light anti-clockwise. So because of this response, we mark the first isomer which rotate the plane polarized light clockwise as plus enantiomer and the second one as negative enantiomer. Now let me explain these molecules in depth, but remember that this is the simple and the basic way of understanding. Whenever we see that the plane polarized light rotate clockwise, the isomer will be named as plus enantiomer, and when it rotate plane polarized light toward anti-clockwise, so isomer will be named as negative enantiomer. Okay, now let me explain about these molecules. Number one thing, when we just compare these two molecules, number one thing we can get that they are mirror images of one another. Okay, if you just remember, I already told you that if I say this one is the carbon, so the carbon atom is bonded with 4 different groups. Here is also the same case. The carbon atom is bonded with the 4 different groups, but though both the molecules are the same. Okay, what is the difference? The first difference I just already told you, they should be mirror images of one another that cannot be superimposed. Okay, what is mean by this superimposed? Okay, let me explain this way. Now let's suppose I have a molecule A. In that molecule A, the carbon atom is bonded with 4 different circles. Now you can see that circle by coloring. Here the molecule B is the same as molecular A, because the carbon the black circle is bonded with 4 different circle, but the circle are the same on as the molecule A, but they are mirror images of each other. Okay, if I try to rotate this molecule B in this direction, so do you think I will get the same molecule A? So answer will be no. Now you can see, if I just rotate this molecule B toward clockwise direction, so I would get this molecule. Now do you think they are same in the space? So answer will be no. So that is the reason we say that they cannot be superimposed. So remember that one thing, they should be mirror images that cannot be superimposed. Okay, and the third thing, or mainly basically when we focus more, remember that the carbon atom, here the criteria is the simple, that the carbon atom should bonded with the 4 different group. Okay, let me explain few more properties of these optical isomers. Number one thing, now you can see, if I start with this, so this one is called plus lactic acid, this one is called minus lactic acid. So what do you think, what is mean by word plus lactic acid? The answer is, it will rotate plane polarized light clockwise, and it will rotate plane polarized light anti-clockwise. So both are optical isomer. Okay, now here we can clearly see the carbon atom is bonded with 4 different groups. Now all these groups are different, so we should have a specific name for this carbon. Now what is this specific name? We call this carbon as chiral carbon. So molecule like this are said to be chiral. The different forms are called enantiomer. So normally we always get molecules having chiral carbon show optical isomerism. Okay, furthermore, the optical isomer can occur when there is an asymmetrical carbon atom. Okay, remember that this chiral carbon is also named as asymmetrical carbon atom. Why we call them as asymmetrical? The reason is the same, because it is bonded with 4 different groups. So as an asymmetrical carbon atom is one which is bonded to the 4 different group, it forms a chiral center. Okay, and the another thing about the optical isomer, that they are chemically identical, although they rotate plane polarized light in different directions. Now I will explain how we configure these optical isomers as R and S. Simple criteria is that the first step, we will identify the chiral center. Second, give each atom connected to the chiral carbon a priority based on its atomic number. That the higher atomic number, the higher the priority. Now there are 4 different groups, and when we talk about the bromine has the highest atomic number. So I will mark this one as group number 1, and after bromine, oxygen, so I will mark this one as group number 2, and after this carbon, I will mark this one as group number 3, and after it hydrogen is the lowest, so I will mark this one as 4. Okay, now in the third step, what I will going to do, I will draw an arrow starting from the priority 1, and I will just connect this one with 2 and 3. So what I will get this kind of arrow. Now do you think this arrow is rotating clockwise or anti-clockwise? So if the arrow goes clockwise, like in this case, the absolute configuration is R. So I will mark this isomer as R. If, as opposed to this, if the arrow goes counterclockwise, or you can also call anti-clockwise, then the absolute configuration will be S. So this is called R and S configuration. If you have any questions, you can ask me in the comments and I will reply.